Good morning. It's exciting to be here, World Automotive Summit on autonomous driving. Who would have thought that 20 years ago or 30 years ago that when the first initiative started on autonomous driving that this would happen? And who would have thought that it would take so long? In the 70s we had much bigger dreams that it would go much faster. Now the exciting format here of the World Summit is that we have different disciplines. 20 years ago we looked at automated driving mainly from a technical perspective, and now we also have legal perspectives. We have here a human factors perspective, and I hope that after the inspiring talk of Brian Walker-Smith you are still encouraged to go into autonomous driving with all the legal aspects, but also his last slide showed that there might be also from a legal standpoint a way to really bring this to reality. Now my job today is to give a perspective on research. Autonomous driving is associated with a lot of uncertainties also, and research, the main task of research is to bring light to these uncertainties, to explore what the options are. And over the last 15-20 years we had a couple of really interesting research projects here that found pieces of the puzzle of this autonomous driving that could really help to bring this vision into reality. But first of all, let me clarify from a scientific perspective, we are not talking about autonomous driving, we are talking about automated driving. So this would be my first modification to this. And automated driving is using autonomous capabilities of machines, but it can also include the human, and we found out that it's quite beneficial to include the human. It's not trivial, but quite beneficial, and we get much earlier entrance scenarios into the market if we include the human. I will give a brief overview over the history of automation, and then we will dive into certain solutions that we have found out over the years. This is not my own, not only my own work, but a lot of institutions were associated with that. For example, the DLR, NASA, Technical University of Munich was funded by the Deutsche Forschungsgemeinschaft, and also a lot of companies, Continental, VW, Volvo were involved in this kind of research. So we already saw a couple of slides from Dr. Höger yesterday and also today on historic situations. Here you see a situation, Champs-Élysées, 1900, and then 8 years later. And of course we had some kind of automation here already, and I will come back to this more sincerely. But what's interesting here is that within 8 years we see that the number of cars has drastically increased, but there are still horse carts here. And if we look at the pure numbers, in 20 years the horse carts went away, but 20 years, that's quite a period. So obviously these revolutions, from a historic standpoint, a revolution, they take some time, and we are also convinced that the trend towards automated driving is also a kind of incremental revolution. And it will take a couple of decades probably, and it will take a couple of what we call migration scenarios. And the migration scenarios is really critical to enable these scenarios in order to enable automated driving. Automation itself did not start in car driving, but started in aviation. Here you see an early example of aviation, very dangerous machines, very skilled people, highly trained, that nevertheless ran a high risk of crashing. And then people start to augment this with radio navigation, for example, to assist this flying. And then automation was already possible in the early 30s and then extended largely in the Second World War. Here the example of the Sperry autopilot. And then a real revolution started towards highly automated aircraft. And of course, over the last 30 years, we also see a tendency towards autonomous aircraft. Here you see the Dark Star aircraft from NASA. That's also now operated by the Department of Defense. But the initial enthusiasm about these pilotless aircraft has dramatically decreased due to the loss of a couple of aircraft, and many planes that you see now on TV UAVs that are called UAVs, uninhabited air vehicles, they are more teleoperated than really autonomously flown by the machine. And most aircraft that we see and that we use also as passengers are highly automated. So most of the time the pilots, the automation is flying these aircraft, but the pilots supervise the automation and can take over any time. And the safety standard of this air system is dramatically good, especially compared to our car and traffic system on the ground. It's orders of magnitude safer. Now, can we copy this development just to the ground? Of course not. There are a couple of specialties here in aviation. It's a much clearer, structured environment. There are no pedestrians up in the sky, no cyclists, so it's easier. But a couple of lessons we can also apply. One of the lessons is, for example, that automation is not a black and white thing. It's not an either or, but it's all shades of gray here between the control of the human and the control of the computer and the machine. And we can identify certain areas of assistance or automation, and this can also be mixed in the same aircraft. Now, if we look into the car domain, it started probably at the same time, but the automation, development towards the automation took a little bit longer, a couple of decades. We have a good trend towards assisted systems. We have a couple of systems that are already, which we would call semi-automated. The adaptive cruise control is an example for that, or also the lane keeping assistance system is an example for that. Here, the example from Honda, that's middle-centered and quite strong already. And then we have a huge development towards autonomous vehicles that actually started in the 70s. Here an early slide from Japan, Professor Tsugawa. Similar examples from Volkswagen. Professor Seifert mentioned this in the 70s. In the 80s and 90s, a big project here in Europe, Prometheus, that was quite a breakthrough. And then our colleagues from Italy, this vehicle you know from the Stanford University that won the Grand Challenge, Urban Challenge, and now every car manufacturer, or almost every car manufacturer, has a car in, at least a research car in the program that is capable of drive fully autonomously, at least for an extended period of time. Here the example of Daimler, the Bertha-Benz drive that was done this year during the IAA. Now, this is the Google car, you all know it. It's technically, from our perspective, inferior to many, many other cars that are developed, especially from the manufacturers, because it's not so well integrated. But it has Google has one big advantage regarding the system. I will mention this a little bit later, why it's really worth to keep this on the map. But what I want to get at is these are technological masterpieces, but not well thought through use cases and not well thought through business cases. We ask the question, where is the driver? What is the role of the driver? And if we look down here, we see most of the vehicles are highly automated, and here we see there's a big gap. So 15 years ago, we started a couple of research programs already. What could be the proper combination of this, and what could fill this gap using this very capable autonomous capabilities together with the driver. And when we started actually not with this nice cars here in the 90s, but due to historic circumstances, we had to start in aviation. Here the situation is you have two well-trained pilots, you have a very complex automation, and the question there was, it was started in the military, if we have only one military pilot, he's not so well trained, how could we group this kind of automation in a way that this can be easily flown? And you were talking about where are the flying cars. Later on we discovered that this technology can also be used for flying cars, so that everybody could just fly this quite intuitively without operating this very complex machinery. And we used a technique that you already know from the personal computer. It's called a design metaphor. On PCs, there was a development in the 70s and 80s that in the 80s we had this command line oriented operating of PCs, and then Xerox laboratory worked out this nice example of the desktop metaphor. So a natural example of a desktop is taken and then applied to this computer, and this enables us to operate our computers, and now, even 30 years later, most of the computers are operated in that way with a desktop metaphor. And we were looking for a metaphor for these highly automated vehicles. To understand very intuitively what it does, what the limits are, and can you guess a natural example, of course not the desktop, but a natural example of a means of transportation that is intelligent, that avoids obstacles, for example, and that you nevertheless can steer very directly, or you can steer it more in an automated way. And the example was already mentioned. The horse is a very, very good example for that. The horse knows something like tight rein, it knows something like loose reins, and many, many more aspects of the cooperation between a highly automated vehicle and some operator, excuse me, and even aspects like platooning or so are already embedded in this domain. And when we started the research, first of all, it was a little bit difficult to get funding, but then NASA put some money on the table and said, this is risky enough, we will do this. And when we started, first of all, on this automation scale, this is tight rein and loose rein. We will need this slide later on. And if you look at the control distribution, you see that in tight rein, most of the control is done by the human here, and only small hints by the machine. And in loose rein, most of the control is done by the automation here. Now, when we started, we did not start with technology, but we started with field experiments. We looked into riding. Everybody of the team had to take riding lessons. And we also looked into horse cart driving, because it's quite a good example. And we tried to drive through the most difficult use cases, for example, to crash this horse cart. Indeed, it's not easy or almost impossible to crash this horse cart. And we tried to ride the horse and the cart up to a wall. And then the horse, of course, started to slow down, started to shake. And then finally it stopped and looked back. And it was very clear what the expression on the horse meant for the driver. So we did, of course, not stop with just this field exploration. But what we found out is that there's a lot of inspiration in this horse domain, where a lot of know-how, how to handle highly automated means of transportation developed over many, many centuries. And then we translated this over years systematically into technical terms. And here we invented a technique in order not to program up things and then wait for many months until the software is ready to test it. We took a member of the design team here and put it on place of this computer and said, you, the member of the design team, please act as if you are the horse, right? As if you are the automation. And we built up what we called a theater method and a theater system. Here you see the operator, the driver, and here we see somebody who is then playing the automation. And these two persons are coupled haptically and can show each other what the automation should do in a certain situation, what the driver should do in a certain situation. And so you could walk through, drive through certain scenarios and make up the design very precisely what this H mode, this haptic multimodal mode of interaction should do in certain situations. And it's a very fast way of doing design, and also doing this design in a structured way so that you can then translate it into software and build up a prototype and then test this prototype. This kind of methodology, the theater methodology, has been copied now a couple of times in a couple of laboratories worldwide. But we, more importantly, for our engineers here, we built up a real prototype, very capable of having a full flight from takeoff to landing, and tested this both with professional pilots who liked this, but also with people who were not pilots. And they were able to fly these aircrafts much easier than today's aircraft. So it would really enable the flying car because it's much easier than today's aircraft. But for you, probably more important, then in 2004, we started to pull this technology back towards the car domain. Here the development had really accelerated. Gernot Spiegelberg, who was at Daimler at that time, had started a big project, Spark, and this was the time then to come back and to see how we can use this technology to fill this gap. And we built up then gradually prototypes also in the car domain. Here you see an example from DLR. We used a side stick here, but don't let yourself mislead by the side stick. The same technology was also applied to the driving wheel. So H-mode, driving with these highly automated vehicles is not dependent directly on the interface. But what's important is that it's a haptically active interface. Here the example with a side stick. And we also developed an automation that is more capable to cooperate with the driver. If you would develop an automation only technically, then you don't have to care about the driver, and it can drive anyhow. But as soon as a human is involved, you need to respect certain compatibility issues. So you need to build up this automation in a way that it's easily understood by the driver and also by somebody outside of the vehicle, by pedestrians, for example. And what we did is we built this technology up in a similar way as we think that the human is built up. So on different layers, a control layer, short-term planning level, maneuver level, and on a navigation level. These are basic models of driving that were developed in the 80s. And we applied this then to the automation. And the trick is to couple the human and the automation on all of these layers on the appropriate way. So on the control layer with a haptic interface, on the short-term planning level, for example, with a head-up display, also on the maneuver level with a head-up display where you see what the automation wants to do and what the driver wants to do. How does this look if you apply this to software? If I can operate this. Okay, here you see an example where a maneuver tree is built up by the machine. It's also built up in a way that it always looks what the driver would like to do and updates this maneuver tree in real time and generates these trajectories. Here you see a situation on the interstate, and then here the driver actually decides to switch the lane, and the automation always updates the options, highlights the most likely option, and the driver can then decide whether he wants to drive in a tight rein or in a loose rein, so lowly automated or fully automated. But he always sees what his automation is thinking in a certain situation. We applied this in simulators, in a couple of experiments. I can only give you a very, very brief insight in the results. But first of all, the subjective acceptance of these different modes, manual, assisted, tight rein, highly automated, loose rein, and fully automated, was in a way that surprised us because the fully automated version was highly accepted. So we expected that people would not like to give full control to a vehicle, but they actually do. And when they trust this automation, they just leave the driving task completely on the side. But highly automated was also quite accepted. What surprised us also was assisted had some problems, because here we used assistance that was a little bit too high, and it's a complete paradigm shift between the assisted or the highly automated mode, because in assisted, everything that the automation does wrong is considered annoying. Here in the highly automated way, a lot of things are accepted what the automation does, because the automation does most of the driving tasks. Quite surprising. Here we see the subjective workload, of course, decreased with the level of automation. The secondary task performance increased. But more importantly, if we just look at these slides, we would come to the impression that fully automated cars are the best. But the whole story changes if we are looking at situations where the automation fails. And let me give you an example here. We see here the fully automated version. Can we have a sound here? Oh, here's the sound. Thank you. Now, she's completely into the secondary task, the automation phase, with a loud beep, and it takes many seconds until the driver takes over and can recover the situation. Far too late here. This would be a very, very strong accident. Here we see the next situation. This is highly automated, so she can also do a secondary task already, but she is coupled here, still in the loop, the automation phase. In a similar way, she just takes over as if nothing would have happened and recovers the situation with no problems. And this is not a singular event, but we put this on a severe test, of course. And here an example of 10 subjects. 5 of them were highly automated, 5 of them were fully automated. And you see the fully automated in red, everybody of them left the road, and the highly automated here in green, everybody of them stayed on the road. So there's a big difference between these two different modes of automation. And one might be legally okay, and the other one might be really difficult from a legal standpoint. Over a couple of projects, we introduced this base research know-how together with the industry and applied this to real vehicles. I will not go into detail, but the Spark event, project is really worth to look into. City Mobile was quite an exciting EU project which started very much on the automated side. I think you mentioned the disruptive technology, the people mover, golf carts on steroids, right? And well, they drive slowly, but they can nevertheless drive highly automated. And there's a big movement in Europe, cybercars, over several projects that exploited that. What we tried is to incorporate this and build a bridge between those vehicles and the car. And what we found out is that the infrastructure is really, really important in order to guarantee a safe operating of the automation. So what we invented here was a concept which we called E-lane, where the lane itself is also certified, and the whole way the lane is set up, whether there are any construction sites or so, is also then structured and organized with a small database and a small car-to-infrastructure link. So from our perspective here, highly automated driving, or what we call partially automated driving, is only possible if you also regard the infrastructure. And that's also the reason why it's so important to look at Google, because Google has a lot of experience and a lot of databases regarding the infrastructure, and also online databases of the infrastructure. Now, even more importantly, the project HAVEit, with partners like Continental, Volkswagen, Volvo, and many, many other research partners, then also looked into this highly automated driving and looked especially at these 3 different levels of automation. We also included this semi-automated, which is the adaptive cruise control, because the marketing people told us they want to have to include this system, and we also find out that it's not a problem to include this on this scale of automation and assistance. So this is what HAVEit addressed. And what we did in HAVEit, we coupled this driver with this intelligent co-system. And the question was how to keep the driver in the loop. That's not trivial, because when driving gets too boring, some drivers might tend to get out of the driving loop and to fall asleep. So we coupled this with a small video camera, which is actually, I think, a Japanese development at that time. The Honda Lexus used this for the first time. It was called Attention Monitor. And here, this is a European development by Continental, observing the driver and finding out whether he's distracted or not distracted. And then the automation is reacting to this and giving hints. And if the driver, for example, is driving in a highly automated mode, so the automation is doing most of the task, which we called loose rein before, and this automation is discovering that the driver is falling asleep, it would warn the driver and then also hand back control back to the driver. And then resist of driving highly automated, because it's crucial here that the driver keeps his supervisory control. Oh, sorry. That's my reminder. I will hurry up. So it's really crucial that we see this automation not only as a stupid thing that drives, but that also that cooperates with the driver and knows something about the driver and really tries to help the driver, even if this means sometimes that the automation refuses to drive in an automated way. So we developed this in a series of explorations and experiments, and the partners of industry and academia implemented this in really nice experimental vehicles. I will not be able to show the movie, but if you are interested in the results, you can go on YouTube and then just Google HAVEit or the HAVEit event, and then this nice movie will pop up and will give you some insight on the HAVEit. Now we are continue working on this topic. We have a German research group on cooperative guidance and control. That's the overall theme, how we handle this automation. We call this cooperative automation. And we are now looking into extending this tight rein, loose rein concept, and we have built up a prototype that includes a new mode. In loose rein, you still have the reins in your hand. So this is called, from the bus definition, partially automated. In secured rein, this is what the horse cart drivers in Vienna do. They just put the reins down, and then they have their hands free and chat and do whatever, and the horse knows exactly what to do. The horse cart drivers do this only on certain roads which are well known by the horse. So this is really secure, and here the driver can also go out of the loop. It's temporarily fully automated. And it's relatively easy to combine from a human factor standpoint. So the solution that comes out there is very natural. You take a fast grip, you have full control, you let the grip loose, you're going in loose rein, and if you take your hands away on the right road, you are in secured rein. If you take your hands back, you are in loose rein again. So very, very natural. You don't even have to press buttons. You can include buttons if you like, but you don't have to. It's highly accepted. We know that it's also safe, it's pleasant. And to sum up, this way of operating with highly automated vehicles gives us a migration path from today's vehicles to this fully automated vehicles, because secured rein, this is like temporary, fully automated. And it's a safe path where you can realize the assistance and automation mode where it's safe, and block out where it's not safe, and only allow, for example, secured rein on roads where it's really safe and that are really secured. And we see this as the future of using the autonomous capabilities and the future of automated driving. In the workshop on human factors, we will go a little bit more in detail on the human factors, especially on authority, ability, responsibility, and control. But due to the time is up. I hope I could give you a fast overview over these 15 years of research that might enable, that gives a couple of pieces of this puzzle of autonomous, of automated driving. Thank you very much.